All right, ladies and gentlemen, today we're going to look at lesson 6.4, dealing with our functions, and we're going to be able to describe them as linear versus nonlinear. And we're going to give some information to you in a variety of forms. So for example, if you have a graph, it should be really easy for you to tell if it's a linear or nonlinear function. If we give you an equation, we're going to give you some information to help you determine if it's a linear or nonlinear function. And then when it's in a data table, we're going to give you a strategy on how to determine if it's linear versus nonlinear function. So first of all, we should know, again, that linear means line and nonlinear means not a line. It's kind of a duh statement. A lot of students are very successful in Chapter 6 on the assessment. A lot of it is just thinking, so hopefully we can get that together. All right, so the graph of a linear function shows a constant rate of change. So if you notice here, this is directly from your textbook, so I'll just zoom in, help us out. We've done this little bumps here. If you notice, they're all changing by 3, so it's increasing by 3. That's constant. Let's see, checking by y, that is also constant. Excellent observation there. So using the idea of a slope again, that would give us a slope of, well, rise, and again, y is rise because that's up and down. So the rise would be negative 8 over 3. Again, it's a constant rate of change. The function is linear, so we would say this is linear. But over here on B, if you notice, all the x's, or the run, would be plus 2 plus, so that part's constant. But looking at the y, it'd be a plus 9, a plus 22, a plus 55. So that means I would have 3 individual slopes. So remember, rise over run. So that would be a 9 over 22. And then you'd also have 22 over 2, which is 11. But we'd also have a 55 over 2. So looking at all 3 different slopes, that is not going to give me a constant idea. The rate of change is not constant, so therefore it's nonlinear. So by doing that information will help you determine, again, if it is going to be constant or not constant, linear or not linear. So let's actually jump to these quick problems. So looking at this here, does the table represent a linear or nonlinear function? So you got 3 to 4, well, that's a plus 1. 4 to 5, and 5 to 6. So it starts off good, but if you remember on our previous one, it didn't. Now, if it's not constant here on the x's, that does not automatically mean that it's nonlinear. You got to continue on. So I've got a plus 1. Oh, computer's freezing. Oops, there we go. So plus 1, this is a, well, if you notice, they're all plus 1. So that means my slope is 1 over 1. Therefore, the rate of change and slope, we're going to use that interchangeably. Rate of change is 1 over 1, so therefore this is linear. All right, let's look at data table B. So let's see here. I've got a 2 to 5. That's an increase of 3. 5 to 8. That's an increase of 3. 8 to 11. Increase of 3. So that's looking pretty good. 4 to 7. That's an increase of 3. 7 to 12. Uh-oh. Increase of 5. Increase of 7. Ooh, not good. But let's double check. The first slope again, remember, rise over run. Rise is the y, so that's 3 over 3, which is 1. The next slope, again, I'm just taking the change here. That's a 5 over 3, which is not 1. And my last one, a 7 over 3, which is not 1. So again, not constant, so therefore we say non-linear. And again, you don't want to make your choice of linear or nonlinear until you've checked it like I've done over here. That will really help you make less mistakes. So again, when we have a data table, we're going to go ahead and check the increase or decrease for the x and y, which again is really just similar to rise over run. And let's erase that. That was messy right there. when we see our graphs, this is kind of like the duh statement. So in other words, these are functions. We are just trying to determine if it's linear or nonlinear. Now, the easiest way to ask yourself is, well, is it a line? So if you have a graph that looks like a line, then it's definitely linear because it's a line. Where if you have a graph that's kind of curved or not a line, we simply say nonlinear. Those are the easiest ones to determine, again, linear or nonlinear. This is not the vertical line test. Vertical line test was to determine if it was a function. This is telling us it is a function. We want to determine if it's linear or nonlinear. So again, when you have a graph, look at the graph. All right, maybe back to the data tables really quick. Remember, you could always pause the video. Let's see, +7. All right, those are looking pretty good. Remember, the X is the run, the Y is the rise. Okay, so this time we're decreasing. Okay, looking pretty good. All of them would be a slope or constant rate of change of -5/7. Looking pretty good. All right, what about this one over here? I've got +2, +2, +2. All right, that looks pretty good. And over here, I've got a subtract 4, subtract 4. All right, subtract 4. That looks pretty good. So that would be, again, rise over run. So rise is y, change in y, so it's -4/2, which is really -2. Excellent. Now, what you might see on your assignment, again, let's say you have your x here. You might have a +3, a +2, and a +1. That does not automatically mean that it is nonlinear. You need to be able to go a little bit further. Oh, looks like I didn't even answer the question. I just found my slope. We kind of talked about it, but let's make sure we actually write it down. Linear. Again, if you only look at the x's, you cannot determine if it is linear or nonlinear. So again, instead of just having the numbers, I'm just talking about the change really quick. So let's say that we have it as a subtract 3, a subtract 2, and a subtract 1. So if I did that correctly, I would have a slope of -3/3, another slope of a -2/2, and I'm running out of room. Let's see. Oops. Come on. Isn't it annoying when technology's not working right? Slowing down. All right, let me erase this stuff here. And we're going to slide this over. All right, there we go. So the other slope, remember that's a positive 1 right there. The other slope is also -1/1. And if you notice, if we were to put all of those in a reduced form, then that would give us a -1/1 or just -1 slope for all of them. So that scenario would be linear. So don't just assume, oh, they're not the same, and make your decision. You got to be able to see it, all that information. All right, so we talked about data tables, we talked about graphs. The last option we need to see is, let's skip, is our actual equation form. Now, some of our phrases that we're going to use might be a little bit different from what you may have expected. So let's see. You can rewrite the equations in slope-intercept form. So you don't even know what that really looks like maybe, but slope-intercept form is y is equal to, so we're going to start with a y, and it's mx plus b, so kind of a preview. So in other words, that one looks good. That one looks good. This one I could use my distributive property, which would give me 4x subtract 4, so that one looks good. This one right here, no, and I call this a funky fraction. We cannot have a funky fraction for linear. So in other words, this one would be the nonlinear, like it's talking about right there. Meaning you can't have your variable at the denominator. Maybe put a little comment there. Variable cannot be at the denominator. Let me type it out for you. Variable cannot be at the denominator. Another one is we cannot have an exponent. So no exponent, really no exponent greater than 1, because it's kind of a basic idea, like x is really x to the first power, but we don't really talk about that. So in other words, if you had something like this, y is equal to x squared, that would be an exponent greater than 1, so that wouldn't work, so that would be nonlinear as well. Again, we're focusing on nonlinear. Another one is you can't have people too close. So let's say we have something like this. 4 is equal to xy. The x and the y are a little bit too close to each other for us. So again, you can't have that double variable. So I'm just going to write down no double variable too close. Because later on we'll learn how to rewrite it, and that would actually look like the funky fraction. So linear is going to be a nice slope-intercept form, y equals mx plus b. Nonlinear is going to be a funky fraction, exponent greater than 1, double variable too close. So again, can't have those too close. So if you have those 3 scenarios, then it's nonlinear. If it looks nice and neat, like a slope-intercept form, then it is linear. All right, we've talked about all 3 different types. I think we can skip that last data table there, and we'll be good. Again, we talked today about being able to determine the difference between linear and nonlinear functions. All right, be awesome.